In this video, I'm going to show you how to determine the optimal solution of a transportation problem using the stepping stone method. The stepping stone method is an iterative technique for moving from an initial feasible solution to an optimal feasible solution. There are two distinct parts to this process. One is testing the current solution to determine if the improvement is possible, and making changes to the current solution to obtain an improved solution. And the process continues until the optimal solution is reached. Stepping stone method is one of the methods used to determine optimality of an initial feasible solution, such as the northwest corner, least cost method, and Vogel's approximation. The method is derived from the analogy of crossing a pond using stepping stones. This means that the entire transportation table is assumed to be a pond, and the occupied cells are the stones needed to make certain movements within the pond. There are several steps involved in this method. Starting at an empty cell, trace a closed path or loop back to the original cell via cells that are currently being used or occupied. Note that a closed path or loop is a sequence of cells in the transportation table such that the first cell is unused or empty and all the other cells are used or occupied with the following conditions. First, each pair of consecutive occupied cells lies in either the same row or column. 2. No three consecutive occupied cells lie in the same row or column. Next, the first and the last of the sequence lies in the same row or column. Fourth, no cells appears more than once in a sequence, or there are no duplication. And last, only horizontal and vertical moves allowed and can only change direction at occupied cells. To start with, we're going to use the northwest corner as a starting feasible solution. In which the initial transportation cost is equal to 4,200. So the used cells are as follows, and we're going to code them as A1, A2, B2, B3, and C3. The unused cells are B1, C1, C2, and A3. So we need to identify the unused cells. So for every unused cells, we're going to create loops or closed path starting from the unused cells and then stepping on stones or on the used cells on a vertical or horizontal movement going back to the unused cells. So for instance, on this unused cell, its loop is from this cell to B2 to A2 to A1 going back to the empty cell. Once the loop has been identified, we are now going to take the sum of each of the transportation cost by assigning an alternating plus minus to this transportation cost. Again, for B1, so that's 4 plus negative 4 plus positive 8 plus negative 5, which is equal to 3. And we're going to do this to all of the unused cells. For C1, its loop is from C1 to C3 to B3, going to B2, and A2 to A1, going back to C3, going back to C1. Again, the movements are vertical and horizontals. Take note, as a trick or as a technique, you can jump over a water or a stone in identifying the corresponding loop. So for this case, we jumped over this empty cell. So the sum of the transportation costs are 3. Instead of adding a negative number, we can directly minus the transportation cost. So minus 5 plus 7 minus 4 plus 8 and minus 5. And this is equal to positive 4. The next empty cell is C2, and its loop is this cell going to this cell, going to this cell, and going back to the empty cell. So the sum of the transportation cost is 3 minus 5 plus 7 minus 4, which is equal to 1. And last empty cell is on this cell, which is A3. So our loop is 9 minus 8 plus 4 minus 7 is equal to negative 2. These numbers, we're going to call them improvement index. If the improvement index are all positive, meaning the solution is already optimal and we can no longer improve the solution, therefore this value will be the lowest transportation cost using this allocation. But since we have a negative number on the improvement index, we can still improve this initial solution. Since the negative number belongs to A3, we can do a redistribution on the loop of A3. So again, on A3, there will be a redistribution of these quantities belonging to this loop that will improve our overall solution. Going back to the signs of the transportation cost for this loop, the positive ones, we'll call them takers, and the negative ones are givers. The quantity that will be taken or to be given by each of this cell and this loop is the lowest quantity with negative transportation cost. So we're going to choose between 200 and 100. So the lower value is 100, meaning we're going to redistribute 100 on the loop of A3. This is negative, so it will give 100 units. This cell will be equal to 0. This is positive, so it will take 100 units. This is negative, it will give away 100 units, so it will be reduced to 100. This is positive, so it will take 100 units plus another 100, which is equivalent to 200. So as you can see, we have redistributed 100 units and maintaining the required demands of each of the warehouses and the capacities of each of the sources. This is still equal to 100. This is 100 plus 200 equal to 300. 100 plus 0 plus 200, that's equal to 300. 100 plus 100 plus 100, that's 300. 200 plus 0, that's 200. And 200 equal to 200. And as an effect of the redistribution, our new transportation tableau would look like this. Before checking if this tableau is already optimal, let's compute for its transportation cost. We are now going to check if this tableau is optimal by checking the improvement index for each of the empty cells. So the empty cells are B1, C1, C2, and B2. The loop for B1 is B1 to B2 to A2 to A1. So that's 4 minus 4 plus 8 minus 5, which is equal to 3. The loop of C1 is C1, C3, A3, and A1, going back to C1. So that's 3 minus 5 plus 9 minus 5, and this is equal to positive 2. On C2, the closed path is on C2 going to C3, going to A3, and going to A2, going back to C2. So that's 3 minus 5 plus 9 minus 8. This is equal to negative 1. And on B2, the closed path is 7 minus 9 plus 8 minus 4, which is equal to positive 2. Since one of the values of the improvement index is equal to a negative number, negative 1, there will be a redistribution on C2. The takers on this loop are C2 and A3, and the givers are C3 and A2. Again, the lower value on the givers is 100 units, which we're going to redistribute on the loop of C2. So this is negative, so we're going to take away 100, equal to 0. This is a taker, we're going to add 100. This is a negative, it will give away 100 units, so the remaining is 100 units. This is a positive or a taker, it will take 100 units, it will become 200 units. Therefore, the third transportation tableau will have the following allocation. And the transportation cost of this tableau is the transportation cost for this tableau is equal to 3,900. And again, we're going to check this tableau if it is optimal. The new cells are the loop for B1 is from this cell going to A1, going to A3, jumping to C3, to C2, to B2, going back to B1. For C1, the loop is from C1 to C3 to A3 to A1, going back to C1. So that's 3 minus 5 plus 9 minus 5. This is equal to 2. On A2, the loop is A2 to C2 to C3 to A1. That's 8 minus 3 plus 5 minus 9 equal to 1. And the loop for B3 is B3 to B2 to C2 going to C3 back to B3. That's 7 minus 4 plus 3 minus 5. This is equal to 1. In this tableau, since all of the improvement index are positive numbers, therefore we can no longer improve this transportation tableau, meaning this table is already optimal, which implies that the lowest possible transportation cost is $3,900. And the allocations from sources to destinations are as follows. From Factory 1 to Warehouse A, 100 units. From Factory 3 to Warehouse A, 200 units. Factory 2 to Warehouse B, 200 units. Factory 2 to Warehouse C, 100 units. And lastly, Factory 3 to Warehouse C is equal to 100 units. And that ends our solution using the stepping stone method.